In this lesson we're going to be looking at using logs and experimental data. Now often where two variables exist, experimental data can be analysed and graphed to find out if there is a relationship or formula to connect the data. And sometimes when we graph that data we can get something that looks like this. And we can see from this graph that there is exponential growth. So the relationship between the variables is that x is growing exponentially. We don't know all the details of it from just looking at this graph, but we do know that it's going to take the form y equals kx to the power of n. We don't know what k is and we don't know what n is, but we know that y is changing exponentially. And we use logs to find out what the k and n are, and therefore we're able to create a formula which will relate this data together. That's what we're going to be looking at now. So if y equals kx to the power of n, we take logs of both sides. We've got log y equals the log of kx to the power of n. K times x to the power of n, I know, can be the result of a sum of logs. So it's going to be the log of k plus the log of x to the power of n. Also know from my third rule that I can move this n, move it to the front of the log. And I'm also at this time going to move the x first. So log y equals n log x plus log k. Now notice there are no bases here with a log. If there's no base with a log, remember it means a base 10. However, I could quite easily have used a base of e and made it a natural log, or in fact any base that I chose. As long as the base is the same for all of them, it wouldn't matter. Now, what I'm looking for here is I'm looking for something of familiar. And I see that this looks a little bit like our equation for a straight line, which is y equals mx plus c. Taking the log of y, instead of m times x, I've got n times the log of x. And my constant term is the log of k. I'm going to just relate those together and see that I've got y is going to be the log of y, m is going to be n, and c is going to be the log of k. If I was to graph these variables, rather than graphing x and y, if I was to graph the log of x and the log of y, instead of seeing that exponential function, I'm going to actually see a straight line. It's going to cross the y axis, in this case log of y, at 0 log k. And I know that because my y-intercept is log of k. Let's have a little look at how we can use this information to solve a problem. We're going to look at an example, then we're going to look at a past paper question. Here's an example. We're given a graph. We're told that it's log of x to the base 10 and log to the base 10 of y. It's a straight line. Crosses here at 1 and crosses here at 0.3. And we're asked to find a formula connecting x and y. So the first thing we're going to do, as it's a straight line, I'm going to first of all find the equation of the straight line. I can see from the diagram that my y-intercept is 0.3. The other thing I need is my gradient. And for that I'm going to need 2 points from the line. I can see one here, that's 1, 0. And I can see one here, 0, 0.3. So my gradient is going to be 0.3 minus 0 over 0 minus 1. And that is negative 0.3. So if I plug these into y equals mx plus c, I will have y is negative 0.3x plus 0.3. And I'm going to now substitute in my logs. So my y-axis is not actually y, it's log to the base 10 of y, and my x-axis is not actually x, it's log to the base 10 of x. So I'm just going to sub these in. Log to the base 10 of y equals negative 0.3 log to the base 10 of x plus 0.3. Now, I want everything to be in log base 10, so I'm going to convert this 0.3, that's going to be log base 10 of 10 to the power of 0.3. So the first thing that I'm going to do here is I'm going to evaluate that 10 to the 0.3. And I get log base 10y is negative 0.3 log base 10x plus log base 10 2. Because 10 to the power of 0.3 is 2. What I'm going to do now is this negative 0.3 is at the front, so using our third law of logs, I know that I can move this to be an exponent of x. So it's going to say log base 10y equals log base 10x to the power of negative 0.3 plus log to the base 10 2. Now I've got the sum of two logs, so I can use my first law, and I know that log to the base 10 of y equals, I'm just going to move this up slightly, log to the base 10 of y equals log to the base 10 of these two values multiplied together. So I'm going to write it as 2x to the power of negative 0.3. And now I'm going to compare the y with what's in brackets here. And I'm going to end up with y equal to 2x to the power of negative 0.3. And that is the formula that relates x and y in this case. What we've got here is a past paper example. This was from 2000. It's paper 2. It was worth 6 marks, all of which were AB marks. Part A. Write down the equation of the line in terms of P and Q. This is a straight line. There's no trick here. The y-intercept is 1.8. I can calculate the gradient using the 2 points. This point here is 0, 1.8, and this point here is negative 3, 0. So I can work out my gradient as being 1.8 minus 0 over 0 minus negative 3, which is 1.8 over 3, which is 0.6. put these into the equation y equals mx plus c, y equals 0.6 x plus 1.8. But what I actually need to do is write it in terms of p and q. My x-axis is not x, it's q, and my y-axis is p. So just make sure you put them in the right place, don't muddle them up here. So p equals 0.6 q plus 1.8. That's the first part of the question completed. Now, it's given that p is log base e of p and q is log base e of q. These are triggers for you here. In part A, it mentioned that this was the result of an experiment, and then in part B, we're actually told that the P and Q are actually log base E of the P and Q. This is how you know that this is the type of question that you're being asked. We need to show that P and Q satisfy a relationship of the form P equals AQ to the power of B, staking the values of A and B. So what I'm going to do straight away here is I'm just going to use the formula that we've just created, and I'm going to substitute in the things that they've told us here. So instead of P, I'm writing down log base E of P, whoops. Instead of 0.6q, it's 0.6 times the log base E of Q plus 1.8. Now I'm going to try and rearrange things using my knowledge of logs. I'm leaving the left hand side alone. I'm using my third log rule to move my 0.6 to become an exponent of Q. So this will be log base E of Q to the power of 0.6. I don't like the 1.8 being there because it needs to also be a log base E, or else I can't do anything with it. And remember, if I've just got a constant and I want to make it log to any base, it just becomes the log of that base of the same, so E to the power of 1.8. And this E to the power of 1.8, I can now just evaluate in my calculator. This is a paper 2 question, it's a calculator question. So I put into my calculator E to the power of 1.8, and I would see that I get an answer of 6.05. Now I see I've got the sum of two logs, so I'm going to use my first log rule to combine those. This was 6.05 times Q to the 0.6. Now I know what I'm trying to do here, and I'm expecting it to come out in a certain form because I've actually been told in the question. So you know you're headed in this direction. So I can now compare what I'm taking logs from each side. On this side I've got P, and this side I've got 6.05 times Q to the 0.6. So therefore P must be equal to 6.05 Q to the 0.6. And that is in fact the relationship, and that's the formula. However, I'm going to check the wording again on the question, and it asks me to identify the values of A and B. So I'm just going to pull those out there. I'm going to say A equals 6.05 and B equals 0.6. Both the example that we looked at before and this past paper are both where the relationship is of the form y equals kx to the power of n. Now, there is another relationship where x is in the exponent, and we'll deal with that separately. After you've watched this video, you need to go back to Edmodo and do the 2 questions that I've put on there based on what you've learnt in this video.